Welcome to Numerical Methods in Economics. Today we'll actually talk about economics. We'll try to use numerical methods to solve a portfolio choice model. The methods we will use to do that is, by and large, numerical integration and optimization. Before I go into details about the actual model, let me just give a few examples of where these methods are used in economics. I mean, this is by no means a complete list of applications of numerical integration and optimization, but just to give you an idea. So it's something that's really frequently arises in economics and econometrics. And as for numerical integration, well, you need to use numerical integration when there's an expectation of a stochastic variable or a function of a stochastic variable. So for instance, expected utility or profits, well, there may be uncertain returns to some investment, or it may be that your portfolio is getting some uncertain return. And in that case, well, then you'll have to solve integrals over stochastic states of the world. That's what we're actually going to do today in our portfolio choice model, where the investor will choose between different number of assets where some of them can have uncertain returns. In order to calculate what is the expected return, well, you need to solve that integral. In order to calculate what is the expected utility associated with a portfolio, well, you need to calculate that integral over the stochastic continuous returns. And then discount utility and profits over a long time horizon in continuous time. That's another integral. Here you would integrate over time. You can do it in finite horizon or infinite horizon. And then in finite horizon, then the limits, say if time starts at 0, the limits would be from 0 to capital T where time ends. Okay, and then that would be an integral with a with finite bounds, okay, or finite limits. You can also have infinite upper bound. So if you have infinite horizons, then you would integrate from say 0 to infinity. Okay, and then calculate what is the discounted value of those returns over a finite horizon or infinite horizon. Moments. Well, integration is appearing so many places in econometrics. For instance, when you want to calculate moments of continuous stochastic variables like, mean, variance, kurtosis, skewness, these are essentially, the moments are essentially functions of stochastic variables where we end up taking the mean. Okay, so that's again an integral. And so you need numerical integration because most of the time, actually, many distributions, once you actually start to take functions of stochastic variables, it's just often the case that you can't express those expectations in closed form. So you'll need numerical integration. Likelihood functions are essentially examples of the same. Bayesian posterior is also the case. You also need numerical integration. So I mean, for maximum likelihood, it's not always the case you can write down the likelihood function, with pencil and paper in closed form and put it into the computer. Sometimes they involve integrals. So prominent examples are some of your parameters, some of your coefficients are stochastic variables. Well, those need to be integrated out. Sometimes you can't really just specify what the probability density distribution is for the variable you're trying to model. Well, you need to simulate it and calculate the you calculate the likelihood function using integration. So I'm not expecting that you get all this. I'm just trying to provide some examples to motivate why we really need to learn how to do numerical integration. Solutions to dynamic economic structural models. Well, that's another example. These are models where agents are trying to optimally allocate resources through time, usually under uncertainty about the future states of the world. So in those equations that describe that economic problem, there's always some expectation operator. There's always some integral. You always need to take expectations and integrate out those stochastic future states of the world. That's another example where you'll need to do a numerical integration, and we'll try to cover, just give some examples of how you actually do that today. So then there's optimization. And how can you, I mean, we're assuming that all economic agents are optimizing, right? I mean, we're using that, we're assuming they're maximizing utility and profits and social welfare. Governments are say, maximizing tax revenue, or social welfare, or whatever objective the social planner have. We assume that firms are maximizing profits and consumers are maximizing utility. How can we assume that the agents are maximizing all this, or optimizing, without being able to, as economists, to solve optimization problems ourselves? So it's kind of it's kind of one of those things that you have to do, right? So there's a flip side of maximization is minimization. So you'll have several examples here. Minimizing of expenses, cost, commute time, carbon emissions, a bunch of things that you would like to minimize. So many objectives when you're trying to find optimal policies, or you're trying to find optimal demand, or when you're trying to find optimal level of investments and optimal. Well, you need optimization routines to solve those problems. It also appears in econometrics, so it's not only for economic agents and for economists. It's when you're trying to maximize, say, a likelihood function. Well, in order to estimate the structural parameters in your economic model, well, you are maximizing the likelihood. You're trying to vary the structural parameters until you get to the top of that likelihood function, okay? Or if you estimate with least squares, like OLS, that's also a minimization problem, right? Well, we just have the solution in closed form, x prime x inverse x prime y. You got that right? So that that's a closed form, but it's not always the case you can get evenly squares in closed form. Sometimes the model is nonlinear, and you need to minimize the squared residuals from your model in order to get your least squared estimate. So that's called nonlinear least squares if it's a nonlinear model. But generally, in econometrics, it's usually about minimizing or maximizing some sample objective, whether it's generalized method of moments, whether it's maximum likelihood, whether it's least absolute deviations, or minimum distance estimators. There's so many different estimation methods. They all require to find the minimum or the maximum of some objective function that's a function of the parameters you're trying to estimate and determined by the data that you have. So optimization and numerical integrations were like key toolkits for the economist, and you really need it because most integrals and optimization problems, they can't really be solved analytically. And without actual knowledge about all this, well, you often be forced to to specify your model and your problem so parsimoniously, so simple that you can do it analytically, and you really end up not choosing the right model because you have to do it on pencil and paper. Now you have computers, you can code Python, you can do so you can do any model that you want and adapt it to your application if you learn all this stuff. Okay, that's kind of that's the motivation. So I think it's going to be clear that you really need to do numerical methods. Okay, so so the plan for this lecture is we want to solve this portfolio choice model, and so we're going to try to illustrate the methods for integration and numerical optimization through the lens of this particular example. Okay, so I'm going to start with a model presentation, and then I'll move on to numerical integration, how to actually calculate the expected value for a given portfolio. So here, just briefly, the agent decision maker, he is choosing between a number of different assets that have uncertain returns, and then he needs to figure out how much do I want to put in each of the different assets. He's doing that to maximize the expected utility, and so in order to calculate the objective function that we are maximizing, we need to calculate the expected utility. That's where we need numerical integration. We'll talk about how to do quadrature, how to do Monte Carlo, both in multidimensional cases and in unidimensional cases. We'll talk about different types of Monte Carlo draws, say random draws. There's something called Halton draws and Sobol draws that are like variance reduction techniques that have, give more precision in your estimates, and a bunch of other different things. Okay, so that's for numerical integration, and then optimization will focus mostly on how to apply Newton's methods in this particular example. You need obviously maximization in order to maximize expected utility. So we'll look at how you actually do that. So first we set up what is the objective function as a function of the portfolio shares, and then we'll try to maximize that expected utility with respect to the portfolio shares, and we'll use Newton's methods. We'll talk a little bit about the importance of using supplying derivatives analytically to the numerical maximization routine, Newton's method, and talk a little bit about line searching and other things. Okay, so why don't we just head on to the economic problem? So this is a portfolio choice problem. I've kind of already alluded to what it's about. It's an investor who allocates his current wealth across n different assets to maximize expected utility. Okay, so that's what we're doing in words. More formally, you can see here's a wealth supposed to be allocated, right? So this is the total amount of wealth to invest, and what you do is that you divide that wealth across n different assets, indexed from 0 all the way up to n minus 1. So we have, I'm starting with 0, and then we're ending with n minus 1. That gives n assets in total, and then omega, well, that's your investment in asset I. So omega I, that's in the investment in asset I, and then you sum all that up, and that has to add up with how much you have to invest. Now you can think, do I really want to invest all my wealth? Well, you can just this is without loss of generality, in the sense you can just say there's an asset number 0 that is the outside option of not investing, say, in risky assets. That's exactly what we're going to do. We're going to say there's a particular asset that we'll say is a risky asset or a safe asset. And you can think of it as not investing. Okay, so this is essentially the budget constraint, right? This is a budget constraint that has to hold. So it's a constraint. So it's, we maximize. What the agent doing is he's choosing all these different portfolio allocations, or how much to invest in asset 0 all the way up to asset number n minus 1, and is doing that in order to maximize expected. So this is expectation operator, expected utility of what? Of the value of that portfolio once the returns are realized. So set here, that's the returns. Okay, so that's how much you get out at the end of the period once the uncertainty is unleashed. So we think of them as like gross returns. And since the prices of each of the assets are kind of normalized to 1 here, you think if I invest omega I in asset I, and then the return is say 1.10. Well, then you get, after that, you get omega I times 1.10. So you get like 10% more than you invest. Okay. So you can think of set I as being 1 plus the interest rate. Okay. And then you essentially just add up all the assets in your portfolio, how much you invested times what the return was, the stochastic future return on asset I. Okay. So that's pretty much it. Utility function is we use a frequently used parametric functional form. It's called the constant relative risk aversion utility function, or just short the CRA utility function. It has this particular functional form. There's an exception for the case where you have gamma equal to 0. In that case, it's going to converge to log utility. Sorry, when it's equal to 1, because then you divide by 0 here. That's actually has a limit of the log, this part here. But yeah, I'll come back to that. The bottom line you need to know at this point is that this parameter gamma is kind of indexing indexing how risk averse the agent is. So if it's positive, then you're risk averse. If it's negative, then if it's 0, then you're risk neutral. If it's negative, then you're really like, to gamble. Okay, so that's like a key parameter. We can most of the time just set it equal to 2, which is kind of just we have to pick something. So like a moderately risk averse agent. We assume that the stochastic future return on the investment I is log normally distributed, and you can write that in this particular way. You say the log of the returns is normally distributed, okay, with parameters mu and sigma here, where mu is the mean and sigma is the variance covariance matrix of the many different returns. Now we have so now set is actually a n-dimensional vector now, right? So this is an n by n matrix, so it's a multivariate normal distribution. If you want to think about, to begin with, just a more simple example, just think about there's only one acid, and then this is going to be the variance, and this is just going to be the mean for that particular acid. But generally, we want to work with multivariate distributions. Otherwise, it's kind of harder to think about how to allocate resources about different acids. Okay, well. That was actually a n-dimensional constraint optimization problem with one equality constraint. This is the equality constraint, so it's a constraint optimization problem, and it's an n-dimensional problem or a constraint optimization problem because we are essentially maximizing over this n-dimensional vector, omega 0 all the way up to omega n minus 1. So we can actually reformulate this as a unconstrained optimization problem. So you can isolate omega 0 and then substitute that in, and then you get what you have right here. Okay, so what I've done here is basically reformulate. I've got rid of the budget constraint by substituting it the implied value of omega 0 into this equation here. So into the equation on the previous slide. So now it's actually a n-1 dimensional unconstrained problem, unconstrained optimization problem. So the agent now chooses omega 1, not omega 0, but omega 1 up to omega n minus 1. That's the portfolio choices. Try to maximize that expected utility that you got here with respect to that vector of parameters. Or vector variables. Then omega 0, well, that's implied by the budget constraints. Once all those shares or all those portfolio choices are determined, so you can calculate omega 0 from wealth and then the remaining investment decisions. Okay, so that's just essentially taking this equation here and moving, taking out omega 0 and move around, and then you get what you have here, and then you just put in omega 0 right here in front of set 0 or set naught. Okay, so this is just to get rid of the budget constraint and try to work with an unconstrained optimization problem. We sometimes set W, the amount of current wealth, to 1. So in those cases, I'm just going to refer to omega i's as the budget or the portfolio shares in asset number I. So yeah, you can put omega I. You can put wealth equal to other things as well in the software that accompany the notebook. but I'm going to refer often to omega i's as portfolio shares, kind of implicitly assuming that this is just normalized to 1. Okay, so what do we need to do numerically here? Well, we need to solve that expectation operator. And in order to solve that, well, we need to specify what is the distribution of those sets. We kind of alluded to it's log normally distributed, but how do you calculate that expectation over that stochastic variable? Well, you need to solve actually an n-dimensional integral. So we'll start simple and look at the case where only there's 2 assets, and one of them is a safe asset. So there's only one stochastic variable, and you need to look at first at a one-dimensional integral. But and then we'll gradually build on from there. What else do you need to do? You need to solve like an n-1 dimensional unconstrained optimization problem, because there's n-1 variables to move around when you're maximizing your expected utility. And again, we can start with a 2-asset case so that basically it's a scalar optimization problem. You just move around omega 1 in order to maximize expected utility, and then omega 0 is kind of implicitly determined by the budget constraint. So that's what we're going to start with. Anyway, before we go there, let me just say a few words about how we parameterize the distribution of asset returns. We're going to assume that they're log normally distributed with variance sigma squared, or sigma, capital sigma, and mean mu. Okay, this is like a vector that's n by 1, and this is an n by n variance covariance matrix. Now we're not going to specify the model in terms of mu and sigma. We're going to, I mean, you could do that, and then the rest of the equations here is kind of, we won't have to bother about those. But I'm just saying that sometimes it's easier or more easy to interpret the parameters of the model if you specify the parameters of the log normal distribution in terms of the mean of the returns. Not the mean of the log returns, but the mean of the returns. Okay, so what is the expected return? So it's say 1.1. Well, then on average, you'll get 10% return to your investment. Okay, where it's less clear what parameter to set in terms of mu and sigma to get that expected return. And then the variance, well, we'll call that sigma squared set. Well, you can say, okay, how much does that return then vary? Okay, now, and then together these two parameters, they determine the shape of the log normal distribution and the implied parameters here. Okay. We also, I mean, since we're assuming they're potentially being correlated, those shocks, we need to specify how they're correlated, and we can specify like a correlation matrix. Okay, so if they aren't correlated, well, this correlation matrix, which is also like n by n, that's just going to be a diagonal of 1s, right? But you can also have correlation matrices where there will be off-diagonal elements that are say positive, in which case you would have positive correlation between some assets. And then together, these 3 sets of parameters, they completely specify what mu and sigma would be. And for instance, you can get sigma, the variance covariance matrix, simply just by multiplying the standard deviations, from the log of the assets on both sides of that variance covariance matrix, and that vector of standard deviations, well, they can be computed basically from the parameters that we have specified. So the expected return Ri on an asset I, and then the variance of the return, the set here. These are the parameters we specified. So once we know those, we can calculate what is sigma I, the diagonal elements of this guy here, and what is what are the means of the log of set, well, you can calculate them by this formula. So in, just to sum up, what you do is you basically you specify what is the expected returns, you specify what is the variance on the returns, and then potentially a correlation matrix. Then you calculate sigma squared and mu by these equations, stack them together into these vectors. Then you calculate the variance covariance matrix of the sigma, and then you got both your mu and your sigma, and then you got have your specification of the log of set. So it's actually it's not that far out. Okay, so you just specify all these equations. Okay, so now let's kind of start with the simplest possible example. I mean, there's a lot of Greek letters flying around here, so why don't we just try to, put some numbers on, not try to attack the problem, the n-dimensional problem, head on right from the beginning. I think I'm gonna, if you do that when you program, you're going to make lots of bugs if you're trying to understand a new problem that's complicated. Try to wrap it down so that you get it as simple as possible. And what do we need here to even talk about portfolio choice? Well, you need at least two assets, right? So otherwise there's no choice. So we're going to work with two assets. We want to have one of them being an asset with a stochastic return, and at least one of them, so that we can work and try to see if we can solve an integral. So we're going to do that, and then assume that the other asset has a safe return. Okay, so basically, in terms of our notation, we can assume that set naught, or asset zero, that's a safe asset. It always gives the return R naught, which we put equal to 1.1. Okay, so you always get 10% return on your assets if you put them into asset number one. Okay, and you can say this is like the outside option, your safe haven. Okay, you put the money in the bank and you get 10%. Very generous bank. So you're probably putting them in the bank, you would be like 0.9 or something. They take the money, your money these days. So these are like just made up numbers, right? But note, there's no variance. Okay, we just always got 1.1. Okay, so you can say the variance is 0. So what we'll call sigma set 0, that will be equal to 0 in this case. Just didn't write it up. And then there's a risky asset with a log normal return, where the expected value of that return is equal to 1.4. So you get like a 40% on average if you put your money into this asset, but sometimes you get knocked over, and the stocks are falling, and you don't get 1.4. You get 0.4 because it's variance on those returns. Okay, but sometimes you can get a lot, like three times your money back. Okay. Again, pretty high returns, but I just wanted to, do it for illustration. It's good to have a little bit of distance between them, so we can see numerically what is going on. So there's a safe asset, there's a risky asset, and then the optimization problem for the investor is the following, right? So here basically you take the expectation of utility of the safe return R naught, and the safe return R naught, and then times omega 0, which is implied by the budget constraint. All you have to invest minus what you invest in the other assets, so that's what you invest in asset 0. Then your investment in asset 1 times the uncertain return in asset number 1, the risky asset. Okay, and then you take the expectation. So what do you need to do here? Well, we need to take this one stochastic variable, right? So this set here is log normally distributed. So we need to take the expectation of this function of a log normal distributed variable. Okay, so that requires us to solve a one-dimensional integral over set 1. Okay, we need to solve a scalar optimization problem. See here, this is just it is no longer a vector, right? There's only one asset or portfolio share to to choose, right? Because omega 0, that's implied by that through that budget constraint. So we need to solve a one-dimensional, unconstrained optimization problem over omega I, or omega or 1. And it makes it easier for us to graph what is the expected utility as a function of omega and, inspect the results. So we're going to start with this simplest possible example first. So all of this I've actually implemented in Python, and you should be able to run this from the notebook that accompanied the video. So why don't we start talking about that? So here, basically, the model is embedded in this, or implemented in this class, this Python class. It's called portfolio. Okay, so we need to import that in order to, to work with to create model instances from this class and work with it. And it has a bunch of different properties and methods that we'll use throughout this lecture. We'll probably need a bunch of other things like NumPy, and then we'll need just a collection of functions that does a little bit of optimization. I mean, we could have used canned routine from SciPy Optimize or something else, but I've just coded up a simple version of Newton's method in a collection of functions that I've collected there in this file called optimize.py that we'll import. And then sometimes we need to take copies of model objects, so we want to use the function deep copy from that module. So that's kind of the code we'll use. So from the portfolio choice model, we can generate an instance, or the portfolio model class. We can create model 1 as an instance from this class. Okay, so why don't we try to I'm going to show you the code just a second, but why don't we just try to see what we have here? Okay, so so the syntax is really, model object equal to portfolio, and then there's a bunch of inputs here, and there's also a bunch of defaults, and you'll have to go into the code because I'm not fully documented this to see what's going on. But one of the things you can do is you can specify what is the mean returns. That's our R from the previous slides. R1 or R0 and R1, they were equal to 1.1. That's the safe return, and 1.4, that's the return, the expected return from the risky asset. Okay, and then they're accompanied by the standard deviation, or the variances of the expected returns, which are 0 for the safe return and 1 for the for the risky asset. Okay. If you do that, well, you can also specify other things like, say, what is gamma? You can have, by default, gamma is equal to 2, but you can also have like gamma equal to 3, in which case it would change the CR utility parameter gamma down here from 2 to 3. But we'll work with the case 2. So this is what we have. So basically, right now the model object is initialized. It has a bunch of properties like, what is model 1 gamma, or attributes, and then if you do that, it prints out what the value of that is. Okay, so this is kind of the way we work with this model object, and it has other things like what is the number of Monte Carlo draws or quadrature nodes. So this is kind of the model object. And here you can see it also calculates what is the mean log returns. It's these mu's, right? These are implied by these two inputs here, so they're not. So say mu is not 1.1, right? It depends on both R and sigma, and through the formulas we saw on these previous slides here, right? So you can actually go in, and so here you got your mu, right? Depends both on R and on sigma, and here they're calculated in this model class. Okay, so these from these parameters here, you can back out where the mean returns are and what also sigma, the standard deviations are. So why don't we just take a brief look at the code. There's no way I can go into details with what is in the code. You have to look and sit and work with it yourself. But here, let me just give you an overview. What are the inputs to the function that initializes this class? You can put gamma, that's the CRA utility function parameter. You can have wealth, that's by default set to 1, but you can have put it to anything. You have to specify the returns. That has to be an array type variable, and then the returns to the standard deviation or the variance of set, or a correlation matrix. Here by default it's just 0, so we assume that the returns aren't correlated, but you can specify one if you want. Then you have to specify what is the number of nodes or number of Monte Carlo draws. We'll come back to that later. What integration method to use, what the seed is of the random number generator if you use that, and then whether you want to print out the output. Okay, so then then it calculates using those formulas outlined before. What are the sigmas? Say here is you got the standard deviation, that's your sigma, and mu, that's those formulas that we just saw on the slide. Okay, so you can go in and compare actually one-to-one to what is the Greek letter saying to you on the slides, and what is the Python code to implementing. Okay. So here, this is just the initialization. Let me see if I can fold the code. So you see there's a bunch of different functions here. There's like the utility function. This is our CRA utility function that we had. I show you just briefly. You can also, there's also the derivatives of the utility, or the second derivatives of the utility that we're going to use. That's going to have the return set. That's written here as a function of what quantile, so you can put in a quantile and then you get out set, and so on and so forth. You got the expected utility, that's doing all the integration. Okay, so that's where all the meat is. Anyway, I'll just go back. We have set up our model, the simple possible case, and let me just go back and clean up here. So with this model, we can plot, say, the distribution of the returns, and here you see the shape of the log normal distribution is skewed to the right. So most of the time you get returns that are below the mean, but then you can get lucky, or below the median, but you can get lucky, you get like a really a good draw, so that you get extremely rich from investment. Like that's actually possible, positive probability mass that you get more your money more than 6 times back. Okay, so that's an example. Then you can move around parameters, if expected returns and so on, and see how the shape of that distribution changes. It's actually not a bad idea to try to work with that. So why don't we just try to see, say we set up the variance to 2, and then rerun this, and then you'll see now the shape is changed, and it kind of get a longer tail out here. But that's things you can work with. I'll get it set back to the values we agreed on, and then move on. Okay, so let's talk about the utility function. Okay, I kind of already alluded to that this was the constant relative risk aversion utility function that has this particular functional form, with an exception that if gamma is equal to 1, then it's 1 plus a log of c. Okay, because you can't divide by 0, but the limit of this function as you let gamma go to 0 is actually going to the log, this part, and then you add 1. That's just a normalization constant, because we want to have it's just nice to have it's normalized, so that if you have 0 consumption for risk neutral agent, then you get 0 utility as well. It's just a normalization matter. It doesn't matter. You can take a positive monotone transformation of any utility function, you get the same behavior. So gamma here is the that's the measuring the degree of relative risk aversion. So if it's negative, then the agent is a risk lover. Okay, you got a convex utility function. If it's 0, you got a linear utility function. You can see that, right? You get c to the power of 1 divided by 1 minus 1 plus 1. Then you just got c, right? So that's just completely linear. And then the case we're going to focus on, where agents are risk averse, that's where gamma is equal, it's positive. Okay, so we're going to work with gamma equal to 2, so like a moderately a risk averse agent. So why don't we try to plot that utility function here, and you can kind of see the shape, how that changes for different parameters. So here in the top, the blue curve, that's for risk loving agent with gamma equal to minus 0.1. And then in the bottom, you got like a very risk averse agent with gamma equal to 3. And you see it's really like a super concave. And so here, this is an agent that really don't like risk, because if you got variability in the return, say sometimes, with some probability you get a return that's close to 0, it really kills your utility, really drops down, whereas you don't get that much out of a high return. Okay, so that's why this function really describes very clearly the risk aversion here. So the more concave, the more risk averse, the more you really just prefer assets that has safe returns. Okay, so that's kind of the CRA utility function. It's widely used in economics. It's really like a workhorse for parametrizing models when you're calculating expected utility. Computing the expected utility. So how do we do that? Okay, now until now, it's just talked about this integral being there somewhere. Okay, and somewhere in that expectation operator. So what do you see here? Well, the expectation operator here, well, that is taking the expectation of a function here of a stochastic variable set. Okay, so this whole thing is just a function of set. Okay, so set is log normally distributed, so it has density G, and written out the density of the log normal density down here. But really what it is it's a function of a log normally distributed variable. So this is a function of set. And how do you calculate the mean of that function? Well, you take the function times its density and integrate over the variable, the support of that variable, which is, for the log normal distribution, is from 0 to infinity. Okay, like it has it's not positive to get negative returns in the log normal here, right? So it goes from 0 on all the way up to infinity. It actually continues right out here. Okay, it's just that the density is pretty low. So that's opposed to the log normal distribution, where the support would be from minus infinity to plus infinity. This has only positive density on 0 and up to infinity. So this is why we integrate over. So these are the limits. This is why we are using these limits in the integral. Okay, we are integrating over the entire support of the random variable set 1, which has support 0 to infinity. Okay, so we need to solve that integral, and I don't have a closed form solution. That's beyond the level of my high school math, at least, to see if I can solve that. So how do we do that? Well, we use quadrature. Okay, so we use Gauss-Legendre quadrature, and I've just chosen Gauss-Legendre quadrature here because it's simpler to think about and will not drown in equations. You could probably rewrite the problem so you'll use Gauss-Hermite quadrature, but then you'll have to deal with the weighting function and all that. Here, it's a little bit simpler. Okay, so we'll use that just for simplicity, but there's one obstacle first, and that is the Gauss-Legendre is in the basic form is used for solving integrals on this form here. Okay, there's no weighting function in front. Okay, This is why we're using this. Okay, whereas you would have like weighting functions for other quadrature rules, like Gauss Hermite, Gauss Lequire, or Gauss. What else do we have? Other quadrature rules. Here, so this is kind of close to what we want, except that the limits are not the right ones. Okay, we have our limits are going from 0 all the way up to infinity. So how do we transform the problem so that we can solve a model in this form? Well, you can easily get it to be a bounded interval from A to B simply by just using a simple change of variable here. And so this formula, that's the formula we're gonna apply. Just a few words about what is in these equations here. So this is the function we're trying to integrate. X here, xi, that's nodes, quadrature nodes. Wi, that's quadrature weights, and we're gonna work with I equal 1 up to to m quadrature nodes and weights. So there's m of them, and then as you increase the number of nodes and weights, well, the approximation is going to be more precise, and actually you can, I think formally, this will perfectly approximate the integral if the function can be approximated by a 2n minus 1 degree Legendre polynomial. And sometimes, and that's then by choosing n higher and higher, well, you can approximate the function more and more closely, and then in the end, you'll approximate almost perfectly, right? So that's the idea. You increase m, and then your approximation becomes finer and finer. It's kind of remarkable that it's just like a weighted sum of the function values evaluated at those nodes, so it's kind of pretty easy to implement. Relatively easy. Things are hard the first time. Well, so we need to deal. So we're almost there, right? We just need to rewrite this so that our function that we can integrate. Our function can be transformed to the domain that is limited between, say, a and b. But what we can do is actually we can transform that stochastic variable set, or we can express that as a function of a uniformly distributed variable, okay? And then integrate over that uniformly distributed variable instead. Well, uniforms, well, they have support 0 to 1, so that's actually going to do it for us. Okay, so I'll look at that right now in the next slide. So you can basically you transform the domain to the unit interval instead of working on the interval 0 to infinity that we have had like here in our integral, right? So we can't work with that directly. We have to transform the problem. So here's what we do. So we're going to use the change of variable so that we can work with a uniformly distributed variable q instead of set directly that's log normally distributed. Because then from those uniform stochastic variable, you can get the log normal distributed variable by this transformation. So how does it go? Well, first, if you take a uniform number and put it into the inverse of the CDF of the standard normal, well, what you get out is the standard normally distributed variable. Just think of these q's here as the quantiles, right? That's what you get when you use the standard normal. You get the quantiles as a function of what the normal variables are. But then the inverse is doing the other way around, so we can give it quantiles and then get out normally distributed variables. And this is the CDF of the inverse CDF of the standard normal. So what you get here, if you put in uniform numbers, uniform random draws here, or uniform stochastic variables here, is you get a standard normal distributed variable with variance 1 and mean equal to 0. Then you can scale that up, because of the normally distributed variable, but just by multiplying with the standard deviation, and then that random variable here from here to here just is standard, is normally distributed with variance sigma and mean 0. Then in order to get the mean of mu1, well, then you add mu1. Okay, so everything you got here in the bracket is essentially is essentially a random, a normally distributed random variable with mean mu1 and variance sigma squared. Okay. Probably I should have had like a subscript 1 here, to make it clear that we're talking about asset number 1. Okay, so basically you can map uniform distributed variables into log normal distributed variables using this formula. And here it works like this for the uncorrelated case. It's going to be a little bit more involved once you have correlation, but we'll save for that for a little bit later in the lecture. So what I've done here is essentially just substitute that in wherever it's set. Okay. So over here. Okay. And then replace the expectation operator over that set. That's actually a bug, right? It should set Q here. I'm taking the expectation with respect to Q. Okay, Q1, right? Copy paste mistake. That expectation, well, that's an integral from 0 to 1 because this distribution has support of the unit interval. I'm not multiplying by the density because this is uniform density, right? So it's just having this this constant density, and you can just it integrates to 1, so you don't really need to write that. And then you're left with a function of an integral of a function of that uniform distributed variable, and this is exactly the form the integrals of integrals we can solve with Gauss-Legendre, right? It's a function over some of some variable integrated from 0 to 1, and this is what we could do with this formula, right? Some function of a variable integrated on a bounded interval. And here our function is just what we have in the brackets up here. You can say this is also the expectation of this function with respect to Q1. So I got to write down here. Okay. Yes. So we'll just move on. How do you implement that? Well, so now we're using the formula, and you can calculate the expectation of the utility for a given value of omega using this quadrature formula, and then we'll integrate from a and b is going to be 0 and 1, so it's going to simplify a little bit, right? So you got 1 minus 0, so that's just 1/2, and then you got 1 minus 0 in here. So it simplifies a little bit. This is 0, right? So and then if the function is just like we had on the previous slide, and then you just calculate that formula. You just essentially need to know what are the quadrature weights and what are the quadrature nodes. Put them into the formula and calculate the sum. Okay. Now we've already initialized what the model. So we have this. We already have in the model. We can print out what the weights and nodes are. Okay. So here, well, this is actually what's already in the model. So this is not making any changes. Let's just put it there so we can potentially change the object. So here's 10 quadrature weights the 10 quadrature weights that you get if you use Gauss-Legendre. These are Gauss-Legendre quadrature weights. We are, in principle, it's implemented as a two-dimensional integral, but I'm really just using one node in the first dimension because there's no variance, so it's never going to be used. It's just going to calculate the expected return always. Okay, so you can see that the way when we get the nodes, well, you put in something here, but once you put that into your function here, right? Like let's see. Once you put that those nodes in here, it doesn't really matter if sigma is equal to 1. It doesn't really matter what Q is, right? So no reason to waste any nodes in the for asset number 0. Whereas you need different nodes for asset number 1 because it's stochastically it's a stochastic variable that varies. And then so here it's integration, the Gauss-Legendre integration nodes, they are all between 0 and 1. But then you can map them into the asset returns through the through this formula for set as a function of those nodes, and then you get returns that are corresponding to the distribution of the log normal distribution. Okay, so here you see you always get 1.1. Regardless of the realization of any shocks, whereas in the for these unsafe returns, well, sometimes you get you lose like 73% of your money. Okay, but you can also get lucky and get the money 4 times back. So that's uncertainty, but on average, this is going to give you 1.4, so 40% on your investment. So I mean, you can see here, very see how these the number of assets, the number of nodes change that, and see how those quadrature nodes change in the different weights. So essentially, that's, you can also do like a 2-dimensional one. So let's say 2 in the first dimension and 3 in the other one. It's not going to change a lot because here there's only a there's no variance on the first asset, so no reason to do that. Anyway, we'll move on. That's a little bit about the weights and the nodes. Okay, so why don't we put this to use? So, and then you want to ask, well, how many nodes do I really need? I mean, that depends on what you're approximating. And it can be hard to know ex ante. So there's good way, there's a good reason to actually check how the precision of your results depends on the choice of the number of nodes n. For the expected utility function, well, the true value of the integral is unknown. We don't really know what it is supposed to, what the result is. I mean, if we knew, there's no reason to do numerical integration in the first place. But then, for the expected return, if you take the expected value of the stochastic variable itself, well, that should be equal to r, and that could potentially give us some indication of how precise various methods are to approximate that mean. Okay, because we know what the results should be beforehand. But the nonlinearity of the utility function, that really affects the approximation of the results. So it's not that you can just look at the expected value of set and how close that is to R1. You need to actually also see how does the approximation change. How does the approximation of the expected utility change as you change the quadrature node, number of quadrature nodes, or number of Monte Carlo draws if you use Monte Carlo. So why don't we try to do that? Let's first just look at the approximation error of the expected returns on each assets by the number of nodes. And here you got the two different assets. This is the risky asset, and this is the safe asset. And you see here, regardless of how many points are used, well, you're always going to get the same approximation, 1.1. Okay, where the true value of the expected return, that's supposed to be 1.4, and you can see it's kind of converging to 1.4 as you increase the number of nodes. And that's actually, worth checking that your approximation method is in place, and that as you increase the fineness of your approximation, it's going to converge to the true value in some test examples where you know what the true value is. So this is a way of assessing at least that you coded up your quadrature correctly and you got the right nodes and stuff like that. So over here you got the approximation error. That's essentially just subtracting the true value, and you can see that it converges to zero, the approximation error, as you increase it up until like 50 quadrature points here. So that's for the expected returns. So we move on and look at the objects of interest, the utility, the expected utility. I mean, recall this is what the agent wants to maximize, right? It's not maximizing expected returns; it's maximizing the expected utility of returns. Okay, so it's like a nonlinear function of the portfolio, of the value of the portfolio. So so that's what we need. So here's just what I'm doing here is I'm plotting the expected utility function, and plotting that against the number of quadrature nodes, and what you'll see here is that that's always also converging, and here you got what is the value here. It's a little bit unfortunate with the scale here, but it says you need to add 1.104 to this number here. This is for gamma equal to 2. So I plotted down here for several different values of gamma. So the blue curve here corresponds to, say, the green curve down here, and so this 1.105, that's where it is down here. Well, it almost looked like we don't really need a lot of nodes. If you compare the different values of gamma, you see there's much more variation across the different approximations. But at least I would say if you do 10, 20 quadrature nodes, you're going to be in good shape here. What really matters, actually, and we're going to look at that later, is does the optimal portfolio, how does that change with the number of quadrature nodes? Okay, that's like another layer of nonlinear function around, right? Solving the optimization problem. So that's one way to do it. That's quadrature. Quadrature has some limitations in high dimensions, and the problem here is really that you need not only to take nodes on one stochastic variables, nodes and weights. Say you need to take the combinations of nodes and weights in all dimensions. So if you have a two-dimensional integral with 10 nodes in each dimension, you get like 100 combinations, right? So you can see where that is going. If you have three-dimensional integral, it's 10 to the power of 3. If you have a five-dimensional integral, 10 to the power of 10 to the power of 5. So that's like a lot. Okay. So alternative, because this has an inherent cursive dimensionality, the computational cost is increasing exponentially in the dimension of the integral. And a really good alternative is using Monte Carlo. And Monte Carlo, the idea behind Monte Carlo is actually pretty simple. It's you sample from the distribution of the stochastic variable, evaluate the function you want to take you want to take the mean of, or you want to take the mean of a function of a stochastic variable. So how do you approximate the mean when you have a sample? Well, you take the average, okay? And then we know by the law of large numbers that the average is converging to the mean. So if these if you have random sampling, and this is exactly the idea, just briefly about what a Monte Carlo is. So you can take a bunch of random numbers, and then just take the average, and that's going to converge to the expected utility as m go to infinity. So here x, that's a an n-dimensional vector with a dimension for each dimension of the integration, or for each asset, if you will, in our example. But for our one-dimensional case, it's just going to be a scale. Okay, each xj, that's just a scale. Then you just draw a bunch of draws, and here our f, that's really already transforming uniform draws into log normal draws, so we can just use the same function and then take a bunch of uniform random draws, evaluating the function, and then average the results. So this is kind of very similar to Gauss-Legendre, except that now the weights are 1 over m, and then the nodes are replaced by random draws from the uniform distribution with the support 0 to 0 to 1, and then if you have an n-dimensional integral, then it's the unit hypercube. So why don't we try to compare this? And see, this we talked about previously. There's several types of draws. You can have random numbers, pure random numbers, or you can have there's techniques to reduce the number of random variables, or to reduce the variance of your estimates. It's called variance reduction techniques, or those draws are also sometimes referred to low discrepancy grids. And examples of this are Sobol draws and Halton draws, and there's a bunch of other draws like Tashiki draws and whatnot. I think the most popular one is Sobol draws, because it has the very good advantage that it's not creating a lot of negative correlation across the different dimensions. Once you get up to higher dimensions, where Halton draws have the problem, and then people shuffle them to get rid of the problem. Anyway, so here's just what I'm doing here is I'm reading in the model. I'm taking just a copy of the model because I'm changing. It's model 1, so I'm just taking the copy of that so I can modify without screwing up what I'm doing below. So I'm just taking a copy of the model instance, and then I change the quadrature rule. Okay, so we consider two different rules: random draws. You can also write like Halton draws here if you want, and then I plot the results. Let's first start with the case where we have a fixed seed, and then we plot the utility function for the expected utility for different different number of parameters. So there's the two graphs here. One is the expected utility of the asset portfolio for approximated by Sobol draws, and there's 3 graphs here for three different values of gamma, and you can see it's kind of flat, right? It's not happening a lot here. Actually, as you increase the number of Sobol draws from between 100 and 5,000. It seems like it's pretty fast converging. Okay, there's not a lot of variation here. Well, there's a little bit of variation in the beginning, but then it's kind of converging. Then there is the random draws, and you see a little bit of variability, and that variability is kind of diminishing as the number of draws increase. And we know that these are the variance of that I've indicated here, the confidence intervals. You can calculate the variance simply just by taking the standard deviation from all your Monte Carlo samples of the function, and then divide by the square root. Then you get like the standard deviation of the mean. And then I've drawn a confidence interval with like the shaded areas like plus minus 2 standard deviations, or 1.96. So it's like 95% confidence interval because we know these are actually normally distributed. So very nice. And then what you see here, this confidence interval was kind of reducing, and we could actually try to increase here, make it a little bit longer. You will see it kind of it takes a little bit of time because I'm doing very many. I'm slicing the interval with only a difference of 100, but you can kind of see that the variance is gradually getting smaller and smaller. Okay, let's put it back to 5,000 just to save a little bit of time. And this is completely flat, right? One of the things that is immediately noticeable is if you I apologize for not aligning the scales here, but at least the scale. The distance between this curve and this curve should be the same down here, and you can kind of see that the variance or the of this estimate is relatively large compared to the distance between the code between these lines here. In this case down here compared to up here. So Sobol draws is really good at reducing the variance on the estimate, and you can actually work with much less draws if you use Sobol draws. And the trick with the Sobol draws is that they're making much better coverage of the support of the distribution we are looking at. They're not just putting the numbers randomly everywhere so that they can tend to cluster together in finite samples. They are, deterministically distributing all these Sobol draws throughout the support of this of the distribution to get better coverage of the integral, and that works really good. So I really highly recommend, for instance, Sobol draws to approximate numerical approximate integrals with this what we call quasi Monte Carlo. Okay, so I don't know. Maybe I should not say much more about this. Well, there's also something called Halton draws. That's just another sequence. So that's a bug, a spelling mistake. Another sequence, and so this replaced the graph with the Sobol draws. So that's kind of the bottom line here is these Sobol draws and Halton draws, they really reduce the variance, and can give more accurate Monte Carlo approximations compared to pure random draws. What you lose, on the other hand, is you don't get for free actually a unbiased estimate of what the error actually is, because these are deterministic draws, so there's no way you can calculate the variance of those. They have no variance. Well, you can probably do a little bit of bootstrapping or something, but that's like yeah. Anyway, so let's move on. So that's kind of now we know how to solve the integral. You can do quadrature, you can do Monte Carlo with random draws or Sobol draws, but how do you find the optimal portfolio share? Well, you need to maximize that expected utility function with respect to the share in asset 1 in our two-dimensional case. So how do you calculate omega 1 star, the optimal portfolio share, the argument that maximizes the expected utility? So in how does this optimal share, how does the behavior, how much do I want to invest in risky assets, change as I change, as the parameters change? Say, for instance, the risk aversion parameter or the distribution of the asset returns. Okay, so we'll look at a little bit of that first. We'll first just do it graphically, and later we'll use Newton's method to solve this problem. So what you can do is simply just plot the expected utility function here. And so what you see here is different graphs where you got omega here, the parameter the portfolio share in asset 1 on this axis here. So as you go to the right, you invest more and more risky. Okay, you go to the left, you put all your money in the safe asset. Okay, then the omega share is 0 here. And then there's a graph for different values of gamma. So you got a very risk-loving agent up here with gamma equal to 1, and then you got in the bottom here, you got gamma equal to 3, so that's a risk-averse agent. And you can see here the top of that curve, that is moving to the left, right? So as you get more and more risk-averse, you invest less and less and less in the risky asset. So more risk aversion, higher risk aversion parameter means you're investing less in the risky asset, okay? Because you don't like risk. So it seems like our utility function is actually capturing what we want here. Okay, so that's like a good model for modeling risk. It does what we expect it to do. That if you increase risk aversion, well, people get less, is willing to undertake less risk and invest less in the risky asset. Okay, so yeah, so that's essentially what we're trying to solve. Okay, that was the model 1. Okay, now we want to move on, and before we go to optimization methods, I want to introduce a model. I want to introduce a model where you have 2 risky assets, because then we can deal with multidimensional integration there. Okay, So what I'm doing essentially, we're just taking model number 1 with the returns explained before, expected returns of 1.1 on the safe asset and 1.4 on the risky asset with variance 1. We take that and modify that problem to a problem where we increase the variance to say 0.5. And now you have like 2 different risky assets, and now we need to think about how to deal with multidimensional integration. Now, before it was like only set 1 we need to integrate out. Now we need to integrate out both set 0 and set 1. This immediately also opened the question: are these returns potentially correlated? Could it be that if set 1 go up, then also set 0 go up, and set 1 go down, then set 0 also go down? If these are correlated, well, it's going to be affecting the investment behavior of the agent, because if the assets are moving together, you can't really just diversify your portfolio by putting your money in either of those 2 assets. It's going to be more relevant where you'll get even more assets. But to think about how to implement correlation, we'll try to do that first. So this problem here requires multivariate integration. It's still a scalar optimization problem because there's only one portfolio share, omega 1, to choose. So we're gradually building up the full model. Okay, so here's the multivariate asset case. For the multivariate asset case, well, really the only thing that changes the way we transform uniform random numbers into log normally distributed random numbers. Okay, before we just had a vector here in front that kind of scaled up all the individual assets. Now we can work with we have the standard deviation, right? There was only one asset, right? So we just scaled up at the standard deviation. Now we need to use the entire variance covariance matrix, and we're not supposed to multiply with the variance, right? We're used to scale up. We scale up by the standard deviation, and in the multidimensional, the generalization of that idea is to take like the square root of the variance covariance matrix. How do you take the square root? Well, we'll do something called like a Cholesky decomposition. So that is the generalization of the square root, in the sense that L here is a lower triangular matrix from the Cholesky decomposition, L times L prime equal to sigma. And then you can verify actually that the expectation of that variable that you get out here is actually having variance covariance matrix the variable here that's transformed this way has variance covariance sigma and expectation mu. And so you just need, there's a function that calculates the Cholesky decomposition of this matrix sigma. But you've also looked at it previously when we had about linear systems of equations. So, this is another application of stuff you've learned. Anyway, so let's move on. So basically now, after this transform, then these sets here are potentially correlated with this variance implied by the variance covariance structure of this matrix here that we specified earlier by specifying the variance covariance matrix. And then the integral, well, now it's no longer a one-dimensional integral, it's like a n-dimensional integral. And now you integrate the utility over all the different assets, all the different sets with respect to this uniformly distributed variable u here. Okay, so I've already made that change of variable and substitute that in. But now it's like a high dimensional integral. How do you do that? Well, you do multidimensional quadrature. Okay, so you can use this product rule, and now a function is now a function of uniform draws or uniform Gauss-Legendre nodes, or it's a function of an n-dimensional vector, right? Because it's n different assets. Like it has n different values of u's, right? This u vector is n-dimensional, right? And so we need to put in like a whole vector here, okay? And then that immediately asks the question: how do we actually construct the grid or the of all these combinations of nodes? And what you're doing is essentially you choose a number of nodes in each dimensions of the integral, and then you take the full Cartesian product of all these. That creates like a big matrix of nodes, and then you evaluate the function in that big matrix of nodes, and then compute the weights. And I don't know, maybe I've actually I have some code somewhere that does it. No, I'm not doing that. I really just encourage you to go in and look at the code yourself here. It's not one of those things that can be a little bit hard to explain, but it's not so hard when you start looking at it. One of the key things to take away here is there's an inherent cursor dimensionality of the problem. Okay, the number of elements in this sum here, see there's a sum for each dimension of M for each dimension of assets. So asset 0, and then all the way up to asset n-1. So it's like there's n elements in this sum, or n summations, and the number of combinations is increasing, or the number of terms in the sum is increasing exponential with the dimension n. Okay, and just to take a very simple example, if you do 2-dimension in each dimension of the integral, so just 2 nodes, that must be the minimum, right? Otherwise, it's hard to capture any distribution if there's no variation. So you take 2 nodes, and then you do that in all of the n dimensions. Well, then you get 2 to the power of n. Right? If you have a 100-dimensional integral, then you have 100 to the power of 100 combinations in the sum. Okay, and it's not. I mean, it's not unrealistic to work with 100-dimensional integrals. But it's impossible with quadrature. And you see here, this number here is big, right? It's something like 1.3 to the power of 30, which is, I think it's called, 1.3 nonillions. Nonillions, that's kind of the step after octillions, so we're kind of far up. It's a big number, okay? So it's like, 1,300 octillions combinations. That's just completely infeasible. That's just not storage on computers to do that, and computer power to do that. And why do we want to waste all this if there's a better method called Monte Carlo? Monte Carlo has the remarkable feature that is totally breaking that cursor dimensionality. You can show that the variance, or the error, the standard deviation of the error, that's converging with root over the square root, 1 over the square root of m, where m is the number of Monte Carlo draws. Okay, the remarkable feature here is that this rate of convergence does not depend on the size of the integral. It's just independent of the size. There's no cursor dimensionality. Okay, and that's because you don't need to do all these different combinations of all these different draws and then add them up. You just draw from the distribution of set, and then average the results, and then the law of large numbers ensure that it's converged, that the mean is converged, the average is converging to the mean, and then the central limit theorem is going to guarantee you that you got it's converging with this square root of n, the rate of square root of n, to your normal distribution with mean equal to the integral. That's pretty cool. So let's break the cursor dimensionality. Okay, so why don't we try to do create our model with these 2 assets, and then try to compare Monte Carlo and whatnot. Okay. So what I've done here is I've created this model and just added this, just essentially changed 0 to 0.5 here. I've also changed the choice of integration method to so-called. And we kind of alluded to the 10,000 point. We're giving a pretty good approximation of that integral. And then you can draw for this two-dimensional integral here. You see, well, I think we kind of already looked at this, right? But this is how the approximation of the expected value function is changing with the number of so-called draws of 0 to 2,000. There's not much happening after 5,000 draws or 10,000 draws. It's just pretty constant. So we'll choose 10,000 draws for this two-dimensional integral. Okay, so now we want to plot the expected utility for model number 1 we had before. That's the one with the safe asset, and then compare it to the case with the risky asset. Where we now introduce a little bit of variance in that safe asset. Okay, so the change here from before is now that the instead of having a safe return that we have up here, we have a slightly more uncertain return with did we have with the variance or the standard deviation? Yeah, so it's a variance of a half. Okay. On the asset 0, and now you can see what happens here is that your investment in the risky asset is increasing. Why? Because the outside option, the safe asset, is now less favorable because there's increased variation on that too. So you can't really just get anything out of that. That's just not. You can't get that safe return. You will have to incur uncertainty on the returns of that too. So then it just becomes much more attractive to take the asset with a higher return, asset number 1. So you see all of them, they're increasing. So these are just small examples from the model. One of the things we want to do now, and we can't just plot all these things, right? We want to see, can we actually find out what these numbers are more precisely? I mean, you can't even see what is on the scale here, right? But but if you take, it's like lambda equal to 2, that's probably around 0.6 or 0.65. It's hard to read, right? We could actually zoom in and see. Okay, why don't we try to plot that for only, say, gamma equal to 2, and then zoom in on the area. It's probably somewhere between 0.5 and 0.70. 0.7. So in this area, that's where the maximum is, and you can see, well, it's nice and concave. It's probably 0.63. That's not a bad guess, right? Yeah. So why don't we just do that? Let's see if we can get that 0.63 with Newton's method. Well, so before we do that, okay, let's talk about how do you solve that using Newton's method? So what is Newton's method? Just a short reminder. What we're interested in doing is maximizing some function, and not to be confused with Newton's method for solving equations. It's very, very similar, right? Because you can just think of Newton's method for solving equations. You can apply that to solving the first order conditions for the maximization problem. Actually, it's equivalent to that if you are not thinking so much about how to choose the step size and what direction to go in and so on. That taking it seriously, you're trying to find a maximum, not just an extremum. Anyway, so here's the algorithm for solving this maximization problem. We want to maximize some function capital F that's a function of variables x1 up to xn. In our case, it will be omega 0 all the way up to omega n minus 1. And maximize that with respect to those variables. Okay, so that's a problem we were interested in. There's an algorithm, and then the algorithm is you start with some starting values, some starting value x0, and now x0 is a whole vector. Maybe a little bit bad notation here, but it's a whole vector of values of x1 up to xn. Okay. So you choose that, and then you choose some stopping parameters. I call them delta and epsilon here. Okay. The first thing you do is you compute the search direction. You can either do that as solving the linear system of equations that involves basically the search direction as the endogenous variable you're solving for, and then the Hessian and the gradients. Okay. And here I've kind of moved it around, but you know, you could also write it as a system of equation where you have multiplied the Hessian here on either side, and then you solve that. I mean, that's more efficient to solve it as a linear system of equations than first calculating the inverse and then doing the multiplication afterwards. It's just easier to, you know, easier to write it in this way here. What is this? Okay, this is the Hessian, the matrix of second order derivatives of that function. So this is like an n by n matrix. This is the gradient, so this is like an n by 1 vector. Okay. Once you got the search direction, you know what to go for each of the different values of x from x naught and to the new value x1. Okay. Let's just forget about step 1 for a second. So this is lambda is step size. Okay, so just put that equal to 1 for now. Then what Newton does is that it just updates the parameter using this Newton step, where you have where you are now plus the search direction times or minus the search direction, and then you get like a new parameter update. So and then you go down here and check, okay, is there any change in the parameters across the two successive approximations of v? Did it convert? Did this x change? If it's so, it's below epsilon scaled by some the norm of the x, 1 plus the norm of the x's, well, then move on here and check if the gradient is close enough to 0 as measured by this delta times 1 plus the norm of the gradient. Here I'm missing you know, 2 vertical bars. When I say norm, I just mean the subnorm or the max absolute deviation. Or the max absolute value here. So if that's satisfied, well, then stop and report success. Otherwise, stop and report convergence to a non-optimal point. Actually, this is what you know, I've implemented here in the optimize code here. So here's what you do. So first, in order to calculate the search direction, well, you need to calculate the function value, the gradient, and the Hessian. And then, so this algorithm is kind of assuming that whatever function you were taking in input and trying to minimize is returning these 3 outputs. First the function value, then the gradient, and then the Hessian. It's doing that if you put the use derivatives to 1. Otherwise, it's assuming that it's only returning the function, and then it's basically using the function. It's using a routine to calculate numerical gradients of that function based on the starting value and the function, and the same thing with the Hessian. And these routines are also in this function. So this is like simplest way of coding up, you know, finite difference approximation of gradients and Hessians. And so you see here what's going on is we're like looping over the different parameters, and then we are perturbing x and x2, and then we're taking the difference and then dividing by 2 times the 2 times the step size here, the step size delta. So that's kind of a finite approximation to the gradient. The same thing with Hessian. Well, then you need to basically loop basically loop once again. So this function is really calculating the gradient of the gradients. So it's calling this other function gradient here. So it's like a double loop over the number of parameters. And you see here, if you have like say 10 parameters, then you would have like to evaluate the function. That's what takes time here, because it requires, for instance, in our case, solving the integral. You would have to do that in the order of a number of parameters squared times. Okay, so it's like quadratic in the number of parameters that the time you need to do this. So that's I mean, you could impose symmetry and save some time. You could probably do forward differences instead of central differences I'm doing here to save time, but it takes time. And the problem is increasing quadratically in the number of parameters, the size of the problem. So we might as well do analytical gradients. So let's, I'll come back to actually how that's computed in just a second. We'll look at it over here. The function we are approximating is inside the portfolio. That's our expected utility function. So it has gradients and Hessians too. But for now, let's just focus on Newton. Okay, so once you got the function values, f, and the gradients and the Hessians, you can do your Newton step. Okay, so g and h, that's corresponding to this is g, that's the first order derivative. So this is h, this is like the Hessian matrix, the n by n Hessian matrix. Once you have that, you can calculate the search direction s. Okay, so in the code, that x is called dx. Okay. So I should probably made like a one-to-one relationship between coding names and names in the slides, but you can make that abstraction. And here I'm doing that by solving this linear system, of the Hessian times the search direction equal to the gradient. Okay. You could also do it like I've done here, with implied by you calculate the inverse of the Hessian times the gradient. But this here is faster, because you don't need to do the calculate actually the entire inverse and do the multiplication afterwards. It's faster, recommendable, and more numerically stable. This part here is about line searching. I haven't talked about that yet, so well. And then there you got, right, what you got here is the Newton update. Okay, so you basically just think of the step as being 1. So you this is where you are now, and then plus the change in x, then you got your new value of x. So this is corresponding to this equation down here. But then sometimes the problem is that this is relying on a quadratic approximation of the of the function we're trying to approximate, and you're maximizing essentially the quadratic approximation. That's what gives you the Newton step. Now, if the function is highly non-quadratic, or you're trying to maximize, say, a convex function, a function that is, you're in a convex area of the function you're trying to maximize, you move in the opposite direction of the gradient. Okay, and that's why line searching can be useful. And then what you're doing is that you're searching along the line of formed by the direction calculated, implied by the Newton, the standard, the pure Newton step. Okay, and then you change some parameter lambda. It's just a scalar parameter, in order to find out, okay, how long do I want to go along this direction? Just changing that parameter. What does it require to calculate? Only the function itself, not the gradients, not the Hessians. Okay, and then you find out what is the optimal step length by solving that problem. You can solve this in many different ways, this line searching problem. I mean, one obvious thing would be just, to choose, why don't you choose a grid, say, between -1 and 2, okay? And then take the one that's the best one, okay? That's kind of a little bit brute force grid search, or even more brute force grid search with finer grids. Or you can use other algorithm like the Gold algorithm, or Brent, or whatever you have. The key thing is that it's taking the best value of lambda that gives the highest increase along the search direction. Okay. For our problem, it's not going to be super useful because we actually have a very well-defined, or very well-behaved problem where the objective function is very smooth and concave, and no convex areas, very closely approximated by the quadratic. So Newton is really good for us, and we're not going to use that line search a lot. Yeah, just want to say, so this is what's going on here, and then of course, depending on whether you are in a maximization, if you're doing maximization or minimization, well, then you would have to either minimize or maximize the function. So here we are doing maximization, so we are trying to maximize the function, whereas if you do it over here, well, then if you're in the maximized world, well, then you would here, this is that minimization routine that I'm using. So I would minimize the negative of the function I'm maximizing. It's kind of like, you can wrap your head around that, but it's a little bit tricky. Okay, so how do we? I mean, Newton requires computing derivatives, right? These second-order derivatives. Until now, it's still kind of an abstract object. We talked a little bit how to compute them numerically, but how do you calculate them analytically? Okay, so the second-order derivatives and the first-order derivatives, these are like n by n matrices or n by 1 vectors. How do you calculate those? And it's really just actually write up the function that you're trying to maximize and then differentiate. Okay, so our function looks, whether you approximate with the quadrature or you approximate with Monte Carlo, it's really this weighted sum of the utility functions, where the utility function is evaluated at these would be like our quadrature weights. If we use quadrature, it would be 1 over n if you use simple Monte Carlo. This CL, well, that's a consumption, realized consumption implied by, say, the Elf Monte Carlo draw. Okay, so how do you calculate that? Well, that's just what is inside the utility function. So it's our omega 1 times set 1, the return to S of 0 for the Elf realization of the shock. Okay. And then the same thing here for all the other assets. Okay. And then you're summing over all those different M Monte Carlo draws or M quadrature nodes. And so this is essentially what we need to differentiate. So if we do that, so here's the first order, the gradient here has the ith element of that gradient. It's like n by 1 vector, remember? That's the derivative of that function with respect to omega I. Okay, the partial derivative. You can do this. So we just, take the derivative of this sum. That's the sum of the derivatives, and then we just apply the chain rule. Okay, and the first part here, that's just essentially constant. Does not depend on omega. It's a little bit confusing with the notation here. We got W for weights and omega for the portfolio shares. So they look very much like each other. So you think that this depends on omega. It doesn't. It's just a constant weight. Okay. What does depend on omega is C, right? Because omega is all over the place in here. Okay. So when I'm differentiating this guy here, you got the derivative of the utility function times the inner derivative of C with respect to omega. So this is like, standard application of the chain rule with differentiation. So let's look at that. So you got it down here. So you got your sum of derivatives, and this is just a constant. The constant times the derivative of the utility function times the inner derivative of the utility function with respect to omega, which is consumption differentiated with respect to omega. And what is that? Well, you got 1 omega I over here that's multiplied with Z naught with a negative in front, and then you got 1 omega I with multiplied with ZI. Okay, so that's what we got in the bracket right here, and all the other omegas, right? Their derivatives with respect to those are just 0. So that's why the sum is disappearing here. then you can just differentiate this expression once more, and again you got you got omega I somewhere and j somewhere in here, so you can differentiate this again. Well, so the second order derivative, or the Hessian, is like an n by n matrix with a jth element being the second derivative of the function with respect to omega I and omega j, a change in both of these two parameters. And now you need to differentiate the utility function again, so it's like the second derivative of the utility function. And by the way, they're written down here. So you got the utility function, the first order derivative of the utility function with respect to consumption, and then the second order derivative of the utility function with respect to consumption. So these are all down here. This is really straightforward, differentiation from high school. So I'll not talk much more about that. So okay. So now you differentiate again, and then we essentially had everything we had before. This is a constant. This is a constant, so we just repeat that, and now we take the derivative of this derivative with respect to omega j. And well, then we essentially have the additional inner derivative inside the consumption here, where it would say omega j somewhere, okay? And that is multiplied with, the set j. So you get exactly what you have. What is this, right? This is kind of a measure of variability in the sets, actually. So it's kind of the variance of those, or the covariances of those sets. Anyway, so these are the Hessians, and you will need to compute those, or it can be a good idea to compute those analytically when you do optimization. Right now we just did a two-dimensional problem, so it's not really a lot of bang for the buck. But in when we can get to high-dimensional problems, you will really see that it makes a difference. Okay, so here's what you get if you put all this together. So I'm calling Newton the routine I showed you from Optimize over here. So yeah, Newton here. And it's taking inputs, the function to approximate or to maximize, and the starting values, and then a bunch of parameters. Okay. The function to maximize, well, that's the function we've drawn so many times, right? So the expected utility function from Model 1 and Model 2. We're going to need starting values, so we call those omega 0. And what I'm going to do is I'm just going to start with a bunch of zeros. Okay, so I'm assuming that the agent is essentially putting all his money in the save asset. Okay, or in asset number 0. You could probably choose better starting values. I just think this is like a conservative guess. It's not like favorite. It's not like I'm assuming the solution or anything. And you can see it's doing iterations. What it's doing here, it's plotting out some output here, and you can see here there's a function here, print out, which is actually is called down here during each iteration. Here it's calling callback. The callback function, so you can specify any callback function you want. Here I'm just as default saying that it's going to use this function here. Okay, so it's printing out what is it printing out? The step length, which is implied by this minimum step. That's what we call lambda on the slides. And it's computing the maximum absolute difference between two successive approximations of the parameter vector, and then it's also calculate the maximum absolute value of the gradients. So that's what's supposed to be 0, and then the function value. And this is what you can see here. Okay, so it's printing out all this stuff. And then it's doing iterations, and so we're starting with this value 0, and then after some time it becomes 0.61, and that gives an increase in the expected utility function. And as we step forward, the gradient falls and falls and falls. You can see this is really quadratic conversions, right? You got doubling of the exponent almost every time. Newton is really powerful to solve this problem here. And then at some point, this is converged to machine precision. The gradient is very close to 0. So I put g tall to it should stop after that's 10 to the norm of the gradient is less than 10 to the power of minus 14. You could stop it before if you want. So let's stop it after once it reaches 10 to the power of minus 8, and then just do fewer iterations. You have to decide. Could we get it with higher precision? Say go to 10 to the power of minus 30. Well, it doesn't really work that way, right? And there's a good reason for it. There's nothing wrong with Newton's method, the theoretical version, but once you start implementing stuff on a digital computer where numbers start with finite number of precision, and I think we're using double precision here that has its 16-digit of accuracy. How can you expect to get 30-digit of accuracy or convergence if you're only using 16 digits? So that's a no-go. Okay, so we have to really work with within the limits of machine precision. So I put it in like to 10 to the power of minus 15, which is already pretty good. Now, I'm using analytical derivatives. Okay. And by the way, let's first look at, before we go into much detail, let's look at what does it give us. So for model number 1, it gives us 0.28, and for the other one, 0.63. Well, is that in line with what we saw in the graphs? Let's go back and take a look. Okay, so we already plotted those functions here, and we're working with a value of a gamma equal to 2. So why don't we just strip the other ones and look at them, okay, separately. So yeah, it looks like model 2 had 0.63. That's not totally out of the blue, and 0.28. Well, that's probably around here. That's not totally out of the blue, and you can you can zoom in and see. Are we actually? It was 6.3, so it was like you zoom even more in and see if So let's go from 6.2 to say 6.4 is the minimum in that area. Well, it most certainly looks like that's the case. So let's look at it here. Yeah, so certainly add that area. So it looks like Newton is really nailing it. Well, I'm just going to put stuff back to basics here, to what we had before, and also I want to so we don't mess up the code. Okay. Okay, so it looks like Newton is really nailing the problem here that we pointed out graphically. So that's good, both for model number 1 and model number 2. The differences in the output is not really huge. One of the things we didn't talk about yet is the choice between analytical and numerical gradients. Okay, so now we're using the analytical ones. Why don't we try to use the numerical ones? Like, first of the things we need to look at, what's the computer time? So 0.6063 seconds. Remember that number. Okay, so 2 zeros and a 6. And then we'll do it again. And first thing to notice here is the many iterations, it's going nowhere. It's just stopping. It's just stalling. The gradient is equal to 0 at the order of 10 to the power of minus 12. Well, it's not because of the precision of the machine, right? We know we have the 16-digit accuracy there, and it was able to nail it with the analytical gradient. So something new is going on. Well, this is because of the approximation error that you get if you use finite difference approximations of your Hessian or your gradients. And of course, these numbers also change with what is the optimal step length and so on, but you got approximation error. Okay, and that approximation error apparently is on the order of 10 to the power of minus 12, so you can't expect this to converge to machine precision if you're not supplying analytical gradients. Okay, so we would have to stop it before, say, oh, that's not even enough, right? And see if it gets closer, Well, it's not like it's totally out of the blue, the result here. You still get these 0.28 or 27.9, so you get the same with the analytical gradients, but it took more time. Before it was 0.06, now it's 0.1. Okay, now in here, you don't really get bang for the buck for the analytical gradients. You don't really get that, right? Because it's a two-dimensional, one-dimensional problem. But in high dimensions, it really makes a difference to use analytical gradients and Hessians. I'm going to put back to default values, so we know where we're going. Okay, so you can also just use a canned routine from SciPy Optimize. That minimizes several different types of algorithms. This is giving the same result. I actually recommend using it. It's just if you want to illustrate Newton's method, well, you need to code it up yourself, and actually trying to go through the steps Newton is important for understanding the properties of it. Okay, so now we can move on to the optimal portfolio choice with multiple assets. So now we're like searching for a whole vector of choices. And we can't draw that on the graph. Well, we could do a 3D graph in a two-dimensional case, but we're gonna just go head on with Newton. So we're gonna analyze the problem with and without analytical derivatives, with and without line search, for different model sizes, with quadrature, Monte Carlo, quasi Monte Carlo. Trying to do a little bit of variations over our themes. Okay, so now we introduce like two new models. It's kind of similar to what we had before. So now the model 3, that's n risky assets with mean returns of all the assets are 1.4. The variance of the returns are 1 for all the assets, and we kind of consider cases with and without correlated returns. Okay, now this is a good test case to see if you got, because we know what the optimal thing to do would be in this case for risk aversion would just be equally dividing your portfolio across these different assets, because they're all the same. Okay, and it's preferable to have your risk diversified by investing in many different assets to just investing in one of the assets. So you're not indifferent between. It's not like you've got a flat objective function. You would put your portfolio shares essential to 1 over n for all the assets. So we have theoretical predictions from this model. Okay, that can be shown. And that goes actually regardless of whether the shocks are correlated or not. Okay. Why am I presenting this? Well, I'm presenting this as a good way, as a good test bed of whether our optimization routines work, whether our approximations with quadrature and Monte Carlo are precise. And to just study models of, computer times as models of different sizes and whatnot, okay? Because we know what the results are expected to be, so we can use this to evaluate our algorithm's ability to actually get that prediction. And then we move on to the more interesting model with one safe asset and n risky assets, and see how the agent is substituting between risk and return in a world with this potentially large series of assets that can be correlated or uncorrelated, in how that affects behavior. Okay, so it's essentially the same as model number 3, but just with a safe return, just like we had in model number 1, with a safe return of 1.1. Okay, so this is like that's model 1, just repeating asset number 1 n minus 1 times. So here's a version. I'm gonna start a little bit from the top here. So we set here parameters that the number of assets. We can try different numbers. We choose a correlation parameter to be the same across all the different assets, and then we build this correlation matrix, which is essentially 1 minus that correlation times the identity matrix plus this correlation factor times a matrix of n by n matrix of ones, So in the case where you have C equal to 0, well, you got the diagonal matrix. If you have the case where C is equal to 1, you've got perfect correlation between the assets. It's just going to be a matrix of ones. And then you got everything in between by varying C between 0 and 1. So we can allow for 0 or positive correlation between the assets. I mean, the model can, in principle, allow for negative correlation as well, but it just becomes a little bit tricky to build a correlation matrix that's meaningful when you have negative correlation, because you can't have all the assets being negative correlated if there's more than 2, because then if asset number 1 is negatively correlated with asset number 2, then it should be positively correlated with asset number 3, right? Because, you know, by transitivity. So so that's a little bit tricky. So we'll just focus on, you know, 0 correlation or positive correlation. Build this matrix in this particular simple way. But you can work, you know, essentially when you want to apply this model, you should download data and calculate what is the correlation matrix and what is the covariance matrix, and then put that into the model. These are just Mega Mouse examples. That's a correlation matrix, and then we generate the same vectors of returns and generate the model object just like before, by saying that the returns are equal to the returns that we have here in the memory. You add an additional argument called, we pass a correlation matrix. We use 10,000 soapball draws, and then verbosity is equal to 1, so we want to print out the output here. The same thing for model number 3, model number 4 is essentially like model number 3, but just with the save assets. So that's very similar, and you can plot them out here. And let's just look at this case here. Look a little bit at the correlation matrices. This is the correlation matrix. It's just a vector of 1 because we have no correlation. And then we can calculate the correlation, this Cholesky matrix L. That's like the square root of the variance covariance matrix that we can build using this correlation matrix and this vector of standard deviations multiplied together on either side. We had a formula on a previous slide doing that, and that gives like just a diagonal matrix with essentially just the standard deviations on the diagonal, because you got to, you know, that's what you get if you got uncorrelated returns. You see all these numbers here, they are identical to the diagonal numbers down here. So why don't we try to see what happens if we put it, say, very closely correlated, so like 0.99. Okay, now you see the correlation matrix looks like this. The Cholesky matrix, well, it basically put all the variances in the first run, and then you got some minor modifications in the other one. So what is happening when you're generating draws is you're multiplying this Cholesky matrix to a matrix of independent random draws, and so when they're very correlated, you're essentially using a lot of weight from the first one. Just thought in the first one is just the sum of all these different independent ones, and then the change in the other assets. Well, they're very much like the first one because they already correlate. So you have smaller numbers here on the off diagonal, whereas in the or on diagonal, right? Because you already accounted for that variance here. Well, you know, that's worth actually sitting down and playing a little bit with. Okay, now we're gonna start putting it back to the case of non-correlation. We have 5 assets as we specified, and let's try to see if we can solve this model. By the way, did we get anything more out here? No. Let's try if we can solve this model. So we're going to use Newton's method again, and to solve this 5-dimensional model, we have like 4 different values of omega, of the starting values of omega. So omega 1, 2, 3, and 4. And then it converges nicely. It produces some predictions here. It says that in the model 3, with there's no save assets, you're close to 0.2, which is the theoretical prediction. and then actually pretty close, I would say. Um, and so that is a prediction here that you get from model number 3. So I would say that's kind of actually pretty accurate approximation. So, you know, there's 5 assets, right? So the predicted share should be the 1 over 5, which is 0.2. In the other model, where there's a safe asset, well, what I calculate here is the share in asset 0, okay? You also got all the other shares in asset 1 up to 4, okay? And they're all the same. So you put the same share in all the different assets. You do that in model number 3. In model number 4, where you have the 1 asset, well, here's the portfolio share in asset 0, and here you got the portfolio shares in all the risky assets. And now here it's actually increasing your portfolio shares in the risky assets, and you have a negative portfolio share in the safe asset. What does that mean? Well, it means that you would actually like to borrow in that asset to invest in the other ones, okay? And we are not precluding that, since we're not putting any restrictions on that those asset shares should be, say, between 0 and 1, or couldn't be negative. So we are allowing the investor to go short in an asset, okay, or to borrow money in one of the assets. And then you would have to modify, you know, the solution method if you want to deal with that problem. We are not doing that. So why is it suddenly so small, this value here? Well, if you go back and see what we had before, you know, with the case with n equal to 2, it was actually not negative, right? It was not negative. Is its portfolio share was 0.72. Now it's suddenly going negative. Why? What is going on? The only thing that happened is we increased the amount of risky assets. They're all the same. Well, the thing is, the subtlety here is that now the investor has the possibility of investing in many uncorrelated different assets, okay? So that makes that pool of investment much more attractive because he can risk diversify his portfolio. So basically, he's reducing his risk by aggregating it. Because if you're losing over here, you can potentially win over here, and then on average, that variance is actually lower. So effectively, what this means is that it's like this combined asset is an asset that is a safer asset than the individual assets when you pull them together. And that makes it much more attractive compared to the case with the compared to the case where you have only one risky asset. You just have to live with that realization of that return. So, you know, the bottom line here is if you increase the number of assets with uncorrelated returns, your investment in that pool of assets is going to increase because your combined, your aggregated risk is reduced, make it more attractive. But now that is stringly dependent on the fact that we are assuming the shocks are correlated. Now, what happens if we put, you know, let's put it back to 0.5. Go over, remember what the number is. So the share in the safe asset in the model where there's a safe asset, that's negative 0.4. Now, what happens if we put the correlation to, you know, 0.9? Now these shocks are very correlated. Okay, so if the return on asset 1 is going to be low, you're going to lose on asset 2 as well with, you know, a high probability. Okay, so they really move close together. So all the assets, they move together like this, okay? Very correlated, okay? So let's consider that case and see how that changes the optimal portfolio share in the safe asset. Now that increases it right back, right? And actually in the limit, it's a perfectly correlated. It's like there's only one asset, okay? So you can't really risk it, diversify your portfolio if you have several different assets. they're all correlated. Okay, it's not like you can aggregate the risk because the risk is moving up, together across all different assets. So that was a little bit about the economics. One of the things, and one thing I want to talk more about now is now we got a 5-dimensional problem here with correlated returns and whatnot. What if, and we're using analytical derivatives for Newton's method? What if we choose to see, okay, how does this affect computer time when we use the numerical derivatives? And you see here we got it already. The answer is 0.5 seconds. And now you see here, now it starts to take time, right? And we have the problem with the precision. So let's go to the 10 to the power of minus 10 in either case. But it's still, each iteration takes time, right? So it converged to a point with a low precision, but it took like 1.5 seconds instead of 0.5 seconds. And then you see here the problem. I'm going to try now with a 10-dimensional problem, and it's going to, I mean, it's not going to take forever. Probably my computer can handle this, but you can see where I'm going, right? This is going to take time, okay? And if our goal is to solve a model with 100 different assets, right? You got to have a Hessian that's 100 by 100, or has 10,000 elements, which is requiring us to evaluate the objective function. Essentially, just if you're doing forward differences, it would be 10,000 evaluations of the expected value, which in turn requires us to solve a 100-dimensional integral. So that's pretty nasty. Okay, so you really want to limit on the computations, and here it's kind of highlighting why it's probably a good idea to put right back those analytical derivatives and get the answer right away. I mean, this is the 10-dimensional optimization problem. You got the answers down here. You can see there's all these different shares. It matches nicely the theoretical prediction of putting 0.10 in each of the assets. There's a little bit of variation. And you got your answer quite quickly due to the power of Newton's method. And even with ridiculous starting values, they are far from the true ones. Okay. So I don't know if there's much more to say about this particular problem. I mean, there's so many things you can do. We got like 10. Well, I guess we should try to do like a 50-dimensional problem here. Why don't we? Okay, it doesn't like to have so many soapball draws. That's a limitation of the soapball draws for this. So let's do random draws. That's another thing. It doesn't like to have so big soapball draws. There's limits on the dimension of the integrals in this particular package. I think actually Deku has some very nice implementations in their own language called Futhak that does actually up to 1,000-dimensional soapball sequences. But Martin Elsman, he knows all about this. We'll just try to do one with standard random draws and see if it can solve it, and it did, and well, you got now probably a little bit more noise in the estimate, but it did solve it pretty fast and pretty accurately. Probably when we're using soapball random draws, we would need more than 10,000 draws. We would probably need like 100,000 draws or even 1,000,000 draws. So, well, I'll just put it back to this base case and then let's move on. So I think that's kind of a little bit of economics, a little bit of numerical analysis. Takeaway is code your analytical derivatives and use Monte Carlo. Okay, so here I want to make a final comparison between Monte Carlo and Quadrature. We talked a little bit about the cursor dimensionality. And so we want to compare and just get a little bit of idea about why this cursive dimensionality is the case is there, and whether you should use like Monte Carlo, random Monte Carlo draws and soapball draws and so on. So we have our model from before. We're going to focus on model number 3 because it's where we know the answer what that should be. So it's better for us assessing the different methods and compare them. Okay, we don't care about so much about the economics right now, just about algorithms. So we have like 5-dimensional problem, uncorrelated returns, and then we have a model just like we had before. Model I call it model MC for Monte Carlo. And then I have model quad for quadrature. Okay, they're just as before, same parameters as model number 3. Okay, now how they're different is the choice of integration method. So here we have soapball draws. Here we have quadrature. Here we have say 1,000 Monte Carlos. So why don't we increase that to like 10,000 soapball draws, and then we have here 10 quadrature points, and here when we specify m, it's really m in each dimension. Okay, so it just repeats that number across all the different dimensions if you just give it a scalar in this case. So really the effective number of draws that you have in this case, or quadrature points, is going to be 10 to the power of n, which in our case is 10,000. So yeah. So and then what I do is I solve for omega using Newton's method, and same thing with the quadrature, and then compare the results. Okay, so you get some results here, and you can see that, well, there were actually quadrature was a little bit slower, basically, I guess, because it had equally many quadrature points. Well, no, it had actually 100,000 combination, right? 10 to the power of 5, that's 100,000. So that's why it was slower. How does it do with respect to getting the approximation right? Well, quadrature is doing pretty good, actually. But here it's essentially an artifact of the issue that we're working with identical assets. So since you're putting the same number of draws, the same nodes in each of the dimensions, it's like it's capturing that all the different assets are the same. Okay, so maybe it's not really the right way to evaluate whether this is a precise approximation. Maybe we should actually see how is the objective function, how precise is that, and then take a look at that. And so here's some code that basically makes a curve where we approximate vary the number of draws, and then draw the objective function as a function of how precise we have the approximation. So I've done here a comparison with 2 parameters just to get the scale right. Okay, so the distance between this curve and this curve should approximately be the same as down here. So this the scale down here is a little bit it's a little bit more spread out. Okay, so one of the things that you can see here is, now down here we got 10,000 draws, right? And over here you got 5. Okay, and this is because we're really only considering Monte Carlos from 0 and all the way up to 10 to the nth root of 10,000, because we need to do basically say if you use 10 points in each dimension, well, you get in total 10 to the power of n points. So we want to have these two kind of add up in terms of how many points that we're evaluating the function in. Okay, so this actually corresponds to each other in terms of how much time it takes to compute. And you can see here with quadrature, it's really still increasing as the number of quadrature points is increasing. And 5 points is not really a lot to capture the log normal. So you can expect this to keep increasing. Whereas for the Monte Carlo, it's pretty constant already from like 1,000 soapball draws. It's not really any significant change. And what is it converging to? Well, it's actually converging to what is you know, here 1.216. Does that 2 1 here? 216, that's around here. So probably, I mean, it seems like they're converging to something like this, the same value, but in terms of the time of computation, Monte Carlo with Sobol jaws just doing this much faster in the higher dimensions. We want to, I mean, to be fair to I'm not saying not to use ever quadrature. Actually, it's really the best you can do in low dimensional integrals that appears in so many places. So let's just do the case with n equal to 2, just for comparison. Do this graph again. And now 10,000 Monte Carlo draws. Well, that's corresponding to 100 quadrature points. This is the same amount of computation that you would do, but you get now 100 quadrature points. And then you can see here our quadrature approximations converging pretty quickly here to this point, to some stationary point. But but you still got a little bit of variance here in this area. So, I mean, quadrature can be quite precise in smaller dimensions, but then it has this cursor dimensionality because you need, if you're using the product rule, you need several points in each dimension, and then it's like the computational complexity is increasing exponentially in the dimension of the integral. So that's really a killer. Okay. I want to try to see if we can do more. I mean, we initially talked about doing like 100-dimensional integral. And here, just forget about quadrature. It's not feasible. Okay, you know, that's the with two quadrature points in each dimension, you would require something like 10 to the power 2 to the power of 100. That's the, you know, nonillion number. Okay, big number, 10 to the power of 30 or something. Okay. So we're not going to do that. That's why I have an exception here for not going beyond n equal to 5, okay? Because it takes time, okay? Let's see what we can do with 10,000 Sobol draws. Just solve a 100-dimensional integral. Oh man, we get a bug. What is the bug? Well, that's the same bug as before. There's a limit on the number of Sobol draws you can do. You have to install Futhak and use their software. So let's do 40. I think that can handle it, or 30. 30, that was possible with this Chaos Pi package. And 30, 1 over 30, that's 0.333. Do we get something that's close to that? Well, it seems like it's pretty much nailing it with 10,000 Sobol draws. Now, if you're doing the high dimensional one, we can still do it with with ordinary random numbers. There's no limits on how many random numbers you can get out of my computer. So we're going to put that to 100, and then write random here. That's the type of random numbers that we're using. And does it solve it? Well, it solves it. But now you start to see noise in the result, right? It did solve this 100-dimensional problem, and it was, you know, it's supposed to be 0.1, but it's almost 0.2. I mean, it's in the ballpark, but you got some assets that are simply just due to finite sample bias. There's limits on how much you can do with 10,000 draws. So why don't we try to, you know, like 100,000 draws and see if it can nail that. I want to actually put the output back, so I'm just going to, so I can see the iterations. Well, we need to probably need to stop it before that's possible. Is it doing iterations? Well, we don't really know. I'm just going to stop the kernel for a second here. So I'm going to stop the code. Try to see if we can get it right back on with the callback function on. You see, it's doing steps. Okay, so it's doing steps, and it looks like it's going the right direction. Gradients is coming closer and closer to 0. Of course, now we are chewing on a 100-dimensional integral and approximating that with a 100,000 Monte Carlo draws. So, I mean, it takes time to evaluate the function, but it's getting there. And you see, it's supposed to be 0.1, and it's pretty close. I mean, it's a remarkable. You got, and all the portfolio shares, I mean, they're not identical. By no means they're identical. But they're kind of in the ballpark of 0.1, all of them, okay? So this is really proving its worth. And if you have a little bit of patience and run this stuff in parallel on a cluster, you can easily do like a couple of million or several million Monte Carlo draws and get very, very accurate approximations of this integral. And so this is, or use the Sopel draws that has very good properties. One thing I want to show, and I'm going to put it back to, like, say, a 10-dimensional. One other thing I want to show you here is, with Monte Carlo, these are random draws, right? So you got also random results. Now, this was, the portfolio share in asset number 0 was 0.10283, right? Let's run it again and see what you get. Well, now it's a new result. So the result in itself is random, okay? Because of the randomness in the way we're solving, okay? And this is because I'm using new random numbers every time I'm calling this. Of course, you can set the seed, but it kind of illustrates that the result itself is a random variable. It has variance, and that variance is actually a measure of how precise our estimate is, and you can back that out by simply calculating what that variance is. So that's another benefit of Monte Carlo. You actually know a little bit about what is the precision of the estimate that you end up with. Okay, so I think it's time to conclude, and so no more details on. Oh man, it disappeared. I think I know this handheld solution is to just go all the way to the end from the top. So I want to just conclude and with a few remarks on what we've been through, just to summarize. Okay, so first some conclusions on numerical methods, and then some conclusions on the economics of the model. So one of the things that we've seen is that the quadratic approximation, the quadrature, is really effective in small problems. Okay, so it really nails the integrals. If you can have, say, if you can afford to have something like 20 quadrature points, you really, I mean, then you can approximate almost any function by a, it's a 2n minus 1 degree polynomial, so that would be like a 40-degree polynomial. That's a really, really good approximation, right? But then the problem is that in high dimensions, well, you have this exponential increase in the number of required points, so sometimes you end up with like 2 or 4 is the maximum, or it's even infeasible in the cases with a 100-dimensional integral. You have this exponential increase in the number of required quadrature points. So the 100-dimensional integral case, that was 2 to the power of 100 nodes and weights, and so that's 10 to the power of 30. That's just infeasible. Okay, at least on my laptop. Monte Carlo totally breaks that cursor dimensionality. It has a rate of convergence that is completely independent of the size of the integral you're trying to approximate. And it's because all these draws, they don't need to be on a regular grid. They just draw from the distribution and then average the result. And then the law of large numbers is giving you consistency in that converging to the true value. And then the central limit theorem is giving you this rate of convergence that is 1 over root n. So that's really powerful. So for high dimensional problems, Monte Carlo is just the best way. That's a method of choice. Okay, you get noise and finite samples, just like we saw in our example just here at the end. We saw how the optimal portfolio shares would change for every time we tried to solve the model. And the same thing, you got this variance around the expected value that you're trying to approximate, these confidence intervals. But you can get standard errors on that, so get an idea of how precise your estimate is. Quasi Monte Carlo, well, that has actually proven to have much lower variance, and so these are extremely effective to compute moderately sized integrals. We had the problem with running out of sobol draws, and I think it's just a matter of that they're not implemented in this package here. I think it's actually, you need state of the art routines like what is implemented in Futhak. To get the libraries that produces sobol draws in very high dimensional problems. But if you have that and get that property of this perfect coverage of the integral, well, then those are really, really good. So it has lower variances in finite samples. The convergence rates does depend on the size of the integral. It's still decaying pretty fast with root n, but it does depend on the size of the integral in this particular formula. So in principle, it's not really breaking the cursor dimensionality, at least for fixed m, the number of grid points. The size of the error is increasing in n. So that's kind of a drawback. In reality, it works pretty good. Optimization, Newton's method seems, a simple and effective method of choice here. Of course, in many other problems, they're not so well behaved as the functions we are looking at here. You will have to use more advanced methods than Newton's. But we saw really clearly the quadratic convergence once we're in the domain of attraction, which is always the case for this function. Line searching, well, I outlined how you could do the line searching by minimizing or finding the step that makes the maximize the function along the search direction implied by Newton's step. And that can be important when the Newton's algorithm is overshooting or even moving in the opposite direction of the maximum, because you're in a convex area of the objective function, or if the function you're trying to approximate is just highly non-quadratic, so that your quadratic approximation that behind the Newton's method is a really poor approximation. It takes you further down than where you started. Okay. Numerical Hessians requires lots of computation, so providing analytical derivatives is really essential. And you saw the changes or the differences in the computer time. In high dimensional problems, it's a difference between very fast and very impossible. So some takeaways in terms of the economics from the portfolio model. The model really captures the risk-return trade-off for the risk-averse agent. These are trivial things, but it's good to see that our objective function captures that the utility function is well specified, that you see that a risk-averse agent invests less than variance increase, that he invests more when the expected return increase, that if you become more risk-averse, you put more money in safe assets, things like that. So we've seen this, and it seems like our model is well specified in terms of describing economic behavior that's very intuitive. When returns of identical distributions, well, the investor divides wealth equally across the different assets. This works as a really good benchmark for a test bed for all the different numerical methods. And one of the things I want to really say here is it's real. You need to use the economics to have some tests on the run. See, you're not making bucks. You need to know both economics and programming and numerical methods to get to produce software that is not having too many bugs and it's actually solving the problem of interest. Okay, and then you can use economics, intuition, and theoretical results to generate special cases where you know the answer. Okay, and then use that as a test bed. That's what we did here with the model number 3 that has n-dimensional assets and a theoretical prediction of, you just spread your portfolio equally across the different assets. That actually applies both when they're correlated and uncorrelated. when the returns are uncorrelated or even negatively correlated, then in the model with the save asset as an outside option, you can't really reduce the risk, or the investor can't reduce the risk by diversifying the portfolio and thereby invest more. Okay, so that's what we saw, that when you have uncorrelated returns and you increase the number of assets, it's really it gives the investor the possibility of risk diversifying by just putting small fractions of his wealth in all these different assets, and then together the aggregate risk of that portfolio is just smaller. Okay, and that makes that together a very attractive asset. The combined asset is very attractive compared to the outside option, the safe asset that has lower return yet no variance. Okay. So it's a way of decreasing the variance by investing in many different assets with uncorrelated returns, or even negatively correlated returns. That's kind of the perfect world for an investor, right? But when they're correlated, you can't do that risk diversification. Okay, so that's not possible. That leads to less investment in the risky assets. Okay, and then the investor would go back to the safe asset. When many risky assets are available, then agent invests less in the safe asset if they're correlated. And then even actually in the case where these assets, the risky assets, become so attractive because of reduced risk or say higher returns, the agent here in this case may even choose to have a negative portfolio share in the safe asset, which is like highlighting here that we are solving a model where we're allowing those assets to be negative. So here we're allowing, economically, we're allowing that the agent can go short in one asset, kind of a little bit like, I'm borrowing by selling that asset on the market. Okay, and then so I'm kind of going short in that asset. Well, that's all I had to say about the portfolio choice model. I think I really encourage you to go and look at the code, work with the notebooks, try to run them one by one, make your own modification, change parameters, change the number of quadrature nodes, change all the different things, make even modifications of this code and say, okay, what if there are not log normally distributed returns but normally distributed returns, or maybe perhaps work with another utility function, or maybe work with another variance covariance matrix, or go out and estimate some covariance matrices and apply this model to your application. I mean, there's many things you can do here. This is just a simple example from economics that kind of shows how rich this the theoretical framework in economics really is, and how well it plays together with solving using numerical methods to implement it on the computer. So bye-bye.